Okay, today we are going to start the next topic, that is equipotential surface. Equipotential surface. It is the part of electrostatics. Equipotential. What we mean by equipotential? Equi means equal, potential means potential. So it is a surface at which the potential remains equal throughout. That is called equipotential surface. So what is it? It is the surface at which the electric potential remains same throughout. Remains same or equal throughout. The surface, throughout the surface. This is called equipotential surface. How can we find it? Equipotential surface. Let's try to understand. Suppose there is a point charge. This point charge Q, and we have a sphere of radius R. What will be the potential due to this charge, point charge Q, on the surface of the sphere? V is equal to 1 upon 4 pi epsilon naught Q by R. And since R is constant of the sphere, charge is also the constant. That's why on the entire surface, the potential will remain same. So this is equipotential surface. You can draw another spheres. These spheres are of radius R1 and R2 are called equipotential surfaces. So these are the surfaces which are equipotential surface regarding the point charge. Similarly, you can take a equipotential surface. Suppose we have uniform electric field in the form of parallel lines, then any plane perpendicular to this plane perpendicular to this, and another plane perpendicular to this is called equipotential surfaces. So these are the examples of equipotential surface. What are the properties of these equipotential surfaces? Properties. Let's try to discuss the properties of equipotential surfaces. One of the most important properties is the work done in moving a charge between any 2 points on the equipotential surface is zero. So the most important property of the equipotential surface is when you move a charge Q0 anywhere between any 2 points on the equipotential surface, then always work done will be zero. Can we derive it? Can we prove it? Suppose a charge is moved from point A to B. Yes, the charge Q0 is moved from here A to B. Then what will happen? WAB, what we have read, is called VB minus VA divided by Q0. What is VB minus VA? This is the potential difference between these two. That is work done per unit charge. Since the surface is equipotential, VA is equal to VB. If it is an equipotential surface, then the potential at point A is equal to potential at point B. Therefore, VA is equal to VB. So left hand side will become 0. So WAB is equal to 0. So there is no work done on moving a test charge anywhere between any 2 points on an equipotential surface. This is one of the important property. Another property is the electric field is always perpendicular to the equipotential surface at any point. If you draw the electric field line, suppose this is electric field line, this is electric field line, these are the electric field lines, various radially outwards, these are the outwards, and every point, this is a tangent, this is tangent, 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 and tangent, and then you will draw the perpendicular. It means electric field lines are always perpendicular to equipotential surface. Can we derive it? Yes, again we can derive it. If you will take it, how much dW is equal to? dW is equal to F dot dr. F dot dr. And what is F dot dr? Is equal to F dr cos theta. And what is F? Q dr cos theta. It is dW. And what about dW upon Q? dW upon Q. This is Q into E. Let me write it Q into E. F is Q into E. And this is a dr cos theta. And if you will divide it, dW upon Q, this is potential difference, E dr cos theta. And since dV is equal to 0, dV is equal to 0. What is dV? Potential difference between any 2 points. This is the work done in moving any charge from point A to P between these 2 points. So if dV is equal to 0, the potential same as then potential difference is 0. So is equal to E dr cos theta. But E and dr both are not 0. Because charge is moved through a distance dr in electric field E, it means both are non-zero. That's why cos theta is equal to 0 or theta is equal to 90. It means electric field lines are always normal to the equipotential surfaces. One more property there, एक और property हम यहाँ से ले सकते हैं, third property, that is these two equipotential surfaces never intersect each other. Because we have read that the electric field lines are perpendicular to the equipotential surface, and if any two lines will intersect, then what will happen? There will be two lines of electric field at point of intersection in two different directions, which is not possible. So these are few important properties of equipotential surface and what we mean by the equipotential surfaces. Okay, come to next. Relation between electric field and electric potential. Now we want to derive a small relation between electric field and electric potential and electric potential. Let's try to develop the relation. Again, consider from here. We have read what is electric field, we have read what is electric potential. Now we will try to establish a relation between these two physical quantities. Both are related to the charge. And let's take an example in which we have a charge which is called source charge, Q, source charge. And another charge is Q naught, as you know it is test charge. I think we all know what is test charge. That is very small as compared to source charge. And we can say this charge, test charge, is kept in the electric field of this charge Q, जिसको हम source charge कह रहे हैं. इसके electric field में ये charge रखा हुआ है. And when this charge is kept over here, then it will experience a force. And suppose you want to move it from distance A to B through distance dr. If it is dr vector and this is vector f, then how much work is done? The small work done to move charge Q naught from A to B, dw is equal to f dot dr. Are we using this relation? Everybody knows it very well. What about force? Is Q naught E vector dot dr vector. If E is the electric field due to charge Q at this point, then work force will become Q naught into E. And what can we write? Or dw upon Q naught E dot dr. And this is small work done divided by charge. Work done pi with charge. क्या डिफाइन करते हैं हम? दिस इज कॉल्ड पोटेंशियल डिफरेंस dv is equal to E dot dr. And if you take potential, then we will integrate it E dot dr. This is another relation. This is electric potential in terms of electric field. ये इलेक्ट्रिक पोटेंशियल है किसके टर्म्स में? इन टर्म्स ऑफ इलेक्ट्रिक फील्ड V is equal to E dot dr. Let's simplify it again. In this case, this is dv is equal to E dr cos theta. Suppose in this case, theta is equal to 180 degree. Force in this direction, dr is in this direction. So what is this? E dr cos 180, that is minus E dr. Or what is E? Is equal to minus dv by dr. And this is known as electric field in terms of electric potential, negative gradient of electric potential. So what is electric field? Electric field is negative gradient of electric potential. Or अगर numerical, if you want to apply numerically, then generally we take this formula. If E is the electric field, V is the potential difference between the 2 points at distance d apart, then electric field will be E is equal to V upon d. So this is E in terms of V and this is V in terms of E. So electric field and electric potential both are related to each other by these two equations. I think it is clear to everybody. Okay, come to next topic. Electrostatic potential energy. electrostatic potential energy. What is the concept of potential energy? When we talk about the work, always we consider energy, either by virtue of its motion or by virtue of its position. If it is by virtue of motion, it is then kinetic. If it is by virtue of its position, then it is potential energy. Consider a very simple case. When this marker is raised from this height to that height, then there is some work is to be done, and this work done is stored in the form of potential energy. And because it is against the gravitational force, that's why it is called gravitational potential energy, जिसको हम MGH कहते हैं. इसी तरीके से अगर हम electrostatic potential energy, when we take one charge and around this charge if we kept another charge in the electric field of the first charge, then either this charge will go away due to the repulsive force or it will move toward the charge due to the attractive force. In both the cases there is a force, there is a displacement, obviously there is a work done, and this work done is stored in the form of electrostatic potential energy. So when one charge, which is called the test charge, is kept in the electric field due to the another source charge, then it will move either towards or away from the charge according to the Coulombian force, as a result of which some work is done in this process, and this work is measured in terms of electrostatic potential energy. Okay, first we try to define in case of 2-point charges. For a system of 2-point charges, for a system of 2-point charges, it is the amount of work done in bringing a charge from infinity to a point in the electric field of another charge. What does it mean? Suppose this is a charge Q, which is called source charge. This is another charge Q naught. Suppose this distance is x and it is moved through a distance dx from A point to B, and at infinity, if this charge Q naught is brought from infinity to any point, then it is called electrostatic potential energy. Suppose this is a point P at which you want to bring it at distance r from the charge Q. So there will be a potential energy. When this charge is at infinity, neither this charge will repel nor attract. So its potential energy is 0. As soon as this charge enters in the electric field of this charge, source charge, then it will experience a force, and as a result of this force, it means it has some potential energy. So when a charge enters in electric field, then it possesses a potential energy. Then how much energy is there? The energy is always calculated by the work done. So in bringing this charge from infinity to any point in the electric field, that is stored in the form of potential energy. So let's try to calculate work done in moving this charge Q naught from infinity to this point, that is called potential energy. Don't get confused with electric potential. There is a slight difference between potential and potential energy. In potential we have defined the almost same definition was there. Over there we have brought a unit positive charge from infinity to this point, but here itself we are bringing the entire body, whole charge of the body, mean the entire body having charge is brought from infinity to that point. Let's try to find the work done. I think it is the case of variable force. If it is the case of variable force, then force will be over there. This charge Q, this is charge Q naught, Coulombian force in this direction, and displacement is in this direction. So what can you do? We can take a small work done, that is F dx cos 180. Can we write it as F in this direction, dx in this direction? What is this angle? 180 degree. What about this? F बताइए कितना हो जाएगा? K Q1 not Q1, Q naught upon x square, and dx obviously with minus sign, cos 180 is minus 1. Okay, total work done from infinity to point P. If you want to bring this charge from infinity to this point P, then how much work will be done? W is equal to minus K Q naught upon x square dx, and that is infinity to R. the lower limit is infinity, and you are to bring this point to charge to point B, which is a distance r from charge Q. That's why you will solve it. Then minus k q q naught minus 1 by x infinity to r, minus minus will become plus q q naught 1 upon r minus 1 upon infinity, always 1 upon infinity is 0, k q q naught upon r, or 1 upon 4 pi epsilon naught q q naught upon r. And by definition, this work done is stored in the form of potential energy. So this is the formula of electrostatic potential energy. This is the formula of electrostatic potential energy, Q Q naught upon R. But it is applicable only for a system of 2-point charges, number 1. Number 2, again it is a scalar quantity. In this case, in this work done, the sign of the charge will be considered in the formula. When you can find potential due to the positive charge, then take the positive sign, and due to negative charge, then take the negative sign, obviously. And if there is a system of more than 2 charges, then what will we do? If we have, it is a system, simplest system. We have derived a formula for the simplest system only for 2 charges. Suppose so many charges are coming from infinity to the electric field of any charge, then what will we do? In that case, we will find the potential energy will be for a group of charges. Potential energy is equal to summation I j 1 upon 4 pi epsilon, obviously constant, q I q j upon r I j. This is for all pairs. All pairs का मतलब suppose you have 3 system of 3 charges, then calculate first for first pair, then second pair, then third pair, and take their algebraic sum. Okay, let me explain with the help of an example. Okay, I am going to apply it in case of, let's apply it in case of a system of 3 charges. How what will be? इसको हम 3 चार्ज के सिस्टम पर अप्लाई करके देखते हैं कैसे आएगा. देखिए, एप्लीकेशन लेते हैं, एग्जांपल लेते हैं. Example first. Suppose is a triangle. Charge Q1, charge Q2, charge Q3. This distance is R12. This distance R23, and distance will R13. What will be the potential energy? That will be A, B, C. What will be the total energy? UAB plus UBC plus UAC. This pair, and this pair. And what about UAB? UAB will be 1 upon 4 pi epsilon naught, which Q1, Q2 upon R12. This is Q2, Q3 upon R23, and this is Q1, Q3 upon R13. So you will apply this formula first in this case, then for this case, and take the sum, algebraic sum, on considering the sign of the charges. One more example we can take. If we have a system more than 3 charges. Second example. If you have a case like this, Q1, Q2, Q3, Q4, R12, R23, R34, R14. This is okay. A, B, C, and D. What about total potential? How many pairs will be there? In the meaning of the pairs, for all pairs. First pair, UAB. Which formula? This formula. K, Q1, Q2 upon R12. Second, UBC, K, Q2, Q3 upon R23, plus UCD, this one, this pair, third pair, plus fourth pair is this one, UDA. Only these 4 pairs are possible. No, there are 2 more pairs are also left. Which one pair? This A diagonal AC. So you have to consider UAC. How will you find it? This K, Q1, Q3 upon this distance AC. One more pair is left. Which one? Q2, Q4. That is plus UBD. So you have to calculate total potential energy for a group of 4 charges, for a group of 3 charges, and for a system of 2-point charges. And there is a simple relation between electric field and electric potential. If V is electric potential, U is potential energy, then U is equal to 1 upon 4 pi epsilon naught Q naught upon R. And what about this? This is equal to V Q naught. So this is the formula for potential and potential energy. So electric potential energy is Q naught times the electric potential. So today we have discussed what about the equipotential surface, what are the properties of the equipotential surface, then what is the relation between electric field and electric potential, and then finally electrostatic potential energy. It's all about for today.